Hi, welcome to video 4.4D, the second fundamental theorem of calculus. Oh, be nice if there was an E there, though. Second fundamental theorem of calculus. No, it's not fitting anymore. There we go. Okay, from the book, if f is continuous, then d dx of the integral from a to x, where a is a constant, of f of t dt equals f of x. Okay, this is what I call the baby version. But basically, if you really think about this, you're taking the derivative of the antiderivative. Doesn't it make sense that they will cancel each other out in some way, shape, or form because the derivative of the antiderivative? Okay, the other thing you'll notice about this, first of all, you're going to have to be on the lookout for d dx of the integral of. Okay, be on the lookout for that. Their version, the lower limit of integration is just a number, 0, 3, 5, root 7, whatever, negative a half. And the top is plain old boring little pretty little x, okay? You'll notice also one of the giveaways is on 99% of the time they'll use t's here, f of t dt. But you'll notice that the answer is the function f, but not at t at that top limit of integration. So let's see how this works. And it's a very simple proof. Let's let the integral of little f of x equal big F of x, which means the derivative of big F of x is little f of x. Then the expression they've given us becomes, if I integrate little f of t, remember, I'll get big F of t evaluated from a to x. Then I'll use the first fundamental theorem of calculus. I'll plug in the top number first and then the bottom number. Then I'm going to take the derivative of the first one minus the derivative of the second one. But keep in mind, since a is a constant, whatever the function big F of x is, when I replace x by a constant, I'm going to get a constant. So the derivative of this constant is just going to be 0, and what I'm going to be left with is d dx of f of x. But of course, d dx of big F of x is what our little f of x is equal to. And therefore, I get f of x. So here's an example. If you have d dx of the integral of, as soon as you see that and you go, oh, look, that's a constant. Oh, look, that's pretty little x. Even no matter how ugly this peanut is, you're just going to take that function and you're just going to replace those t's by x. The end. Okay, there's no plus c because ultimately you're taking a derivative. Here's another example, d dx integral 2 to x of 7 to the t over sine t dt, because that's d dx of the integral of, so it's second fundamental theorem of calculus, because that's a constant and that's just x, your answer is going to be this function, but take the t's away and replace them with x's. Same thing here, d dx integral constant to x, take this function, replace the t's by x's. It's extremely simple. So here's an example. They give you big F of x is this integral, and they ask you to find the derivative of big F of x. So you're finding the derivative of big F of x, which is the integral from 3.07 to x of this ugly thing. Again, notice that it's the derivative of the integral, so second fundamental theorem of calculus. Notice this is a constant. Notice this is just x. Your answer is simply that exact function that you see, but replace all the t's by x's. Okay, now the book for some reason doesn't have the expanded version of the second fundamental theorem of calculus, which is what happens if the lower limit of integration is not a constant, but it's something else, and what happens if the upper limit of integration is not x, it's something uglier than x, okay? This is actually pretty simple. It looks tricky, but it's not. Remember how we used to replace t by whatever was up here, which used to be x? Well, now you're going to take the t and replace it by h of x. But keep in mind you are taking a derivative, right? Which makes sense that since this is ugly, you would have to use a chain rule times the derivative of ugly. And then the minus is because before this was a constant, and when we took the integral, we got a function, we evaluated it at the constant, we got a constant, we took the derivative of a constant, we got 0. But that's not going to happen anymore. So it should make sense to you that we're back to the first fundamental theorem of calculus, which is f of the top minus f of the bottom. So this will be minus f of the bottom ugly thing, and again, because of the chain rule, times the derivative of it. Okay, and of course, here's the proof of all that happening again, as you can see. Now when it comes time to do this, it's going to be a chain rule. Same thing here, it'll be a chain rule. and therefore you get the answer I got. Okay, so here's an example. What's d dx of the integral from sine x to x cubed plus x of t squared dt? Again, up to you to notice that this is second fundamental theorem of calculus. So the answer is going to be this function where I replace the t by the top guy times the derivative of that top guy minus, and then I'm going to take this function, replace the t by the bottom guy, which is sine x, times the derivative of sine x, which is cosine x. Okay, here's another one. You're going to replace the t by x. So you're going to have x cubed, derivative of x is 1, minus, and then you're going to replace the t by negative x, and then times the derivative of negative x chain rule, which is negative 1, and you'll get 0. Okay, this is like number 94. I know this looks weird because these look like rectangle squares and they should be rectangles. But anyway, so you've got this function, which is this should be an empty dot here and an empty dot here. But you've got these three blue segments, okay? And it says use the graph of the function f. So this is the function f of t. This is t, this is f of t. And the function g, where g of x equals the integral from 0 to x of f of t dt. What they mean by that is g of 1 is the integral from 0 to 1 of f of t dt. G of 2 is the integral from 0 to 2 of f of t dt. G of 7 would be the integral from 0 to 7 of f of t dt. And what they're asking you to do is complete the table, okay? So here's 1, here's x, here's g of x. So g of 1 is the integral from 0 to 1 of f of t dt. So if I go from 0 to 1, then I have this green region right here. It's a rectangle, width 1, height 2. 1 times 2 is 2. 0 to 2 is just another one of those rectangles, also width 1, height 2. So 2 plus another 2 is going to be 4. G of 3, and now you can start accumulating, because g of 3 is the integral from 0 to 3, but isn't the integral from 0 to 3 the integral from 0 to 2 plus the integral from 2 to 3? Now we already know from 0 to 2 is 4, so I already have that this is 4, and then minus the integral from 2 to 3. Now the reason it's minus is because from 2 to 3 the region's below. So again, this is a 1 by 2. The area of the rectangle is 2, but the value of the integral is negative 2. Okay, etc., etc., etc. You're just going to keep on going. And then you're going to take what you've accumulated so far, and then you're going to add from 3 to 4, which is minus another 2. And then you're going to add plus from 4 to 5, which is minus another 2. And then same thing from 5 to 6, subtract another 2. Now you're going to start adding positives. This is a 1 by 3, which is an area of 3. So you're going to add 3, again, add another 3, add another 3, add another 3. So you're not actually figuring out each one individually, you're accumulating them. Okay, now it asks you to plot those points. So if I plot those points, the point 1, 2, the point 2, 4, the point 3, 2, the point 4, 0, I'm just taking these actual x and y coordinates here and plotting them. You'll see that I get this graph for g. Where does g have its minimum? Well, the minimum is going to be at 6. Okay, as far as why that is, come on. Okay. Okay. Because you'll be able to explain that your first derivative is positive between 0 and 2, negative between 2 and 6, and positive between 6 and 0, right? Okay, which you can see right here. So that means your g is increasing, decreasing, increasing, and that's why it's going to have a min at 6 and a max at 2. When does g increase at the maximum rate? That would be from 6 to 10. That's when the slope is the steepest. The zeros of g, in other words, when is g of x equal to 0, which is when is the integral from 0 to x of f of t dt equal to 0, and that happens at x equals 4 right here. Here's another similar kind of question. It says g of x equals the integral from 0 to x of f of t dt, where f is a function whose graph is given below. And it's asking you to estimate g of 0. So g of 0 is the integral from 0 to 0 of who cares what, that's 0. Next thing is estimate g of 2, which is the integral from 0 to 2. So if you look at that, that's going to be the negative area of this right triangle right here, which has a leg of 2 and a leg of 4. So 1/2 2 times 4 is 4, but it's below, so it'll be negative 4, etc. G of 4, you can then start accumulating and say, well, I already have 0 to 2 is negative 4. So negative 4 plus another negative 4 is going to be negative 8. Then I'm going to take negative 8 and I'll add from 4 to 6, which is a trapezoid. And then you can figure out the area of the trapezoid to be 6. And then you're going to add 6 again to that for this next trapezoid, which is congruent to that trapezoid. Where is G increasing? G is increasing whenever G prime is positive. And in other words, wherever F is positive, because F is equal to G prime. And you can see that F is positive between 4 and 8, right? And it's negative between 0 and 4, so you can tell where G is increasing and decreasing. Relative extrema, of course, you can tell because if decreases then increases. And a rough sketch, again, I'd be taking those points and plotting those points. And